Welcome back to Unit 1. This is limits. This is the second video I have, which is evaluating limits analytically. Let's begin by the first method of evaluating limits, which is plugging in the value. So whenever you have a limit, you should always immediately jump to plugging in the value unless it's obvious that you can't do that. So for this one, limit x approaches 2 of x squared plus 1, you can plug in the 2 there, and you see that it'll give you just an answer of 5. Notice in the second image, there is no limit notation before the expression. That is because when you actually plug in the number into the variable, you do not need to write the limit notation. However, every step that you take where you still have x in there or y in there, depending on whatever the letter is that you're using, you have to keep writing the limit notation beforehand. That is important on the AP exam if you have any sort of limits, if you have any sort of limit questions, or in any sort of calculus exam. This is not just for AP. So here are some properties of limits. If you have the limit as x approaches a of some constant, c is a constant, times f of x, you find the limit. You can take it individually. So the limit as x approaches a of some constant is just going to be that same constant because the constant is just always the same, times the actual limit of f of x. That's the L is the solution. So you just multiply the constant times the solution of your limit x approaches a of f of x. When you're doing addition and subtraction, you just take the limits individually. You can take the limit x approaches a f of x, limit x approaches a g of x, and then you just add those two solutions together at the very end, or subtract them. When you're doing quotient or product, which are these two right here, you do pretty much the same thing when you just multiply or divide them at the end, except with quotient, you have to make sure that the bottom does not equal 0, because that would lead to an undefined answer. So that cannot be possible. When you're factoring rational limits, this is another way to do it. This is something that you'll typically do when a solution is, or when the solution that you get from the original one is indeterminate. So indeterminate form is like 0 over 0, infinity over infinity, negative infinity over negative infinity. So as you see there, I plugged in 2, I did our original plug-in method, and it failed because we got the indeterminate form. And that actually means that usually when you get indeterminate form, there's another way to solve it. So what I did is I factored it down, and I see that there's a common term on the top and the bottom, which is x minus 2. So what we're going to do here is we're going to factor those out and then cancel them out on the top and the bottom, and that'll leave you with the limit as x approaches 2 of x over 2x plus 1. Now notice how I kept the limit notation beforehand, before the actual expression there, because we still have x in the expression. We didn't, plug in the 2 into there. And once we do that, we'll see that our answer is 2/5. So a problem that seemed impossible at first there with the indeterminate form actually is possible, and we see that the answer was 2/5. Thank you.